Setting precise angles for woodworking. For DVDs, drawings, tools, and project articles, please visit my website at AmericanFederalPeriod.com. Hello, I'm Rob Millard, and welcome to my shop. In this video, I want to talk about the testing or laying out of angles. And when I think of an angle, I think of anything other than a right angle, but of course that is an angle too. And every woodworker has various squares for doing right angles for the laying out and checking of those. And I would imagine that almost every woodworker has some way to lay out and test a 45-degree angle, the most common miter. But once you get past that, it gets a little less clear-cut and a little less accurate when you lay out angles. And I'm currently working on a project that is a small octagonal table. And so of course you have the either 22.5 or 67.5 degree angle for the miters, depending on how you want to look at that. And when you lay those out, you've got 16 miters. So if you're off even a fraction of a degree, in total that's going to be a significant amount. So you got to have a way to really get a good angle on your layout, because enough is going to go wrong when you cut those angles, the wood movement and that kind of stuff. The more accurate you set up the initial cut, the less hassle you're going to have when you go to glue that together. So I want to run through some of the common ways and some of the less common ways to lay out the angles in a home workshop. When setting angles, this is the first tool that comes to mind, and this is the one I've had the longest. This is the protractor head to the ubiquitous combination square set. And I've had this since 1989. It's a Starrett, so it's a high quality one. And the last time I actually remember using it was in 1990 to set the angle on some rafter tails on a remodel job I was doing. So that I give you a bit of an idea of the kind of accuracy I expect from it. And I'm surprised at a tool that's always included in machinist sets that it's not more accurate, or that it's as common as it is. And the fatal flaw is, and I'll show that to you in just a second, is the scale and the way that it reads. This is the reason I don't like this tool. And that is that small gap that you see here at the pointer between the index mark on the fixed part and this rotating scale, the protractor scale. That makes it very difficult to line it up accurately. And what I usually end up doing is looking at it obliquely and trying to eyeball it on one of the index marks, or sometimes try to, if I'm looking for something that's a half a degree, like 67.5 degrees, trying to eyeball a half a degree. And it just has never worked out too well for me. It's a really cool tool to look at, but not very practical in my experience. Next on the list is this, which is a step up in accuracy and a step way down in price. This is a machinist protractor. This happens to be a Lufkin. And I got this on eBay and haven't cleaned it up yet. It's in really good shape, but it could stand some polishing and waxing. But you can immediately see the advantage of it. The index mark overlaps the protractor graduations, or the angle graduations. So there's no parallax effect in reading this. Now the downside to this is the length of the head is fairly small, so you don't got a lot of bearing surface there, and that could lead to some inaccuracies, but it's not too bad. And this actually can produce pretty decent accuracy because the diameter of the scale is somewhat larger than on the protractor head for the combination square. So setting half-degree angles is certainly practical, and maybe even quarter-degree angles, although that's a bit of a stretch. Now, on a similar one to this that I don't own is a Bridge City Tool version, and it's a work of art with a price tag to match. I don't know if they're still in production, but a friend of mine has one. And being very much larger, the graduations are consequently farther apart, and you could get a very high degree of accuracy out of it. So that's a tool to consider. Next up is this, and this is, for me, the most practical method. This is an angle gauge set. I bought this on eBay. It's made in China. And despite its high precision, it's very inexpensive. I think this was less than $35, including shipping. And this is the expanded set that includes a quarter and a half degree block. And then in addition to that, it has 1 through 5 degrees in 1 degree increments. and then 10 through 30 in 5-degree increments. So with this, you can set any angle from 1/4 of a degree up to 90 degrees in 1/4 degree increments. And I took these to a machine shop that I used to work at to have them magnetized, but it didn't really work so well. But say we're wanting to do the 22.5 degree angle. Well, there's a mark on there denoting which portion of a degree it is. So always keep those face up. Got a 1/2 degree, 2 degrees, and 20 degrees. And now we have a 22.5 degree angle, or a 67.5 degree angle, however you want to look at that. And this is very, very accurate, far more accurate than you would probably need for woodworking, but it's so quick and easy, every woodworker should have a set of these. This humble tool, the sine bar, is the ultimate in angular accuracy. I worked part-time in a machine shop for nearly 8 years, and I don't even recall hearing about a sine bar, let alone seeing one in use, but they are common in machine shops. And it's a very simple concept. You have a bar of steel here that, when it's resting on these 2 rods, is perfectly parallel to the surface it's resting on. And those rods are spaced a precise distance apart, in this case 5 inches. And this is not a commercially produced one. This was made by a machinist, and I purchased this on eBay very inexpensively. But they can be bought new made also inexpensively or very expensively, depending on what you want to spend. But they all have the same common traits, and all of them would be more than accurate enough for woodworking. And that distance being spaced precisely apart, that becomes the hypotenuse of a right triangle. And you can stack various heights on the other end and come up with a precisely calibrated angle. So let's look at the different ways to achieve that stacking. I'm going to be demonstrating using this granite surface plate, but you certainly wouldn't have to go to this ridiculous extreme for setting the angles. The surface of your table saw would be more than accurate enough, and probably your workbench would be too if it's flattened to the degree it should be for woodworking. It's just that this was only $26, and I bought it at a Woodcraft for lapping plane bases flat. Now this method is one that I have never seen anywhere else, because I just kind of came up with it. I already had this height gauge, and I wanted to be able to set that height to whatever dimension I needed. But the problem is that this scriber point is in the way, and it references off this bottom edge of this scriber point here. So I needed something that was equal to the height of that scriber. So I went to the machine shop where I used to work, and they ground this little piece of steel for me. I could have done the same thing with a file and got it accurate enough for what we're doing here, but being ground, it's within 1/1000th of an inch of being accurate. So I just reversed the scriber so that that's back away from it there, and leave this piece sticking out. And so now, because these are the same thickness, they cancel each other out, and I can dial the height that I need mathematically here on this scale and set the angle. So that's the first way. Now we'll move on to another way. This is the most common way to set the height of the sine bar. Now in a machinist setting, they would use gauge blocks. These are spacer blocks. Gauge blocks are ground a little bit more precisely and come in a greater variety of combinations than this. But with this set, you can go everywhere from 1/10 of an inch up to a full inch in 1/1000th of an inch increments. So it's a very versatile set, and also inexpensive. I spent less than $30 on this on eBay, but they're available brand new for around $40. And this is another tool that I think every woodworker should have. And we'll come back to this and see how you use these to set the height of the sine bar. Up next is a combination of tools, a 1, 2, 3 block, and a set of adjustable parallels. And like everything else in this video, it was either purchased at flea markets or on eBay. The 1, 2, 3 blocks were like $7 for a set of 2. It was more to ship them than they were worth. And they are a very precisely ground piece of steel, obviously 1 inch thick, 2 inches wide, and 3 inches long. And they've got holes drilled in them both to lighten the steel and also so that you can bolt them to each other or to fixtures. And these are a very common tool in the machine shop. And then the other part are adjustable parallels. I've got a set of 4 here that go from fairly narrow up to fairly wide. There's an expanded set that goes from real narrow to wider yet, and that consists of 6 of them. And these are really kind of neat. They're dovetailed, and they've got a set screw in them. And within the range that they can move, you can get any number, an infinite number of widths out of this by measuring across here. So what you would do is find out how high you need your sine bar to be tilted up at the one end, and set this dimension with a caliper or a micrometer, and then tighten the set screws down and put that on there, and then put the well, I'd have to have it up like that, but put the sine bar on there and get your proper angle. And we'll look again at this in greater detail here in a minute. The final way we're going to look at for setting the height of the sine bar is using this, which is a planer gauge. This is again a machinist tool, and I got this at a flea market for 20 bucks with some accessories in a neat box. And this is a Lufkin, so I'm guessing it's probably from the 40s or 50s or maybe the 60s. And it's a variation on the adjustable parallel. What you have here is a wedged shaped dovetailed sliding bar that can be slid in an infinite number of sizes within its range. And it can go from about a 1/4 inch, and I think it can go up to something like maybe 5-6 inches. I'm not exactly sure how high that is, but it's beyond the capacity of a 5-inch sine bar, so it has plenty of range of motion. And what you would do here is determine what your height setting is, and then with a micrometer or a dial caliper, set the height or the width, however you want to look at that, of this, and then you can put your sine bar on there and get your angle. And so now we'll go ahead and go through each of those methods and show an actual angle being set. There are a couple categories of tools used for setting angles that I don't have examples to show you. And within those categories, there's some subsets of tools for setting angles. First, there's digital implements. And these can be a digital protractor or a sliding T-bevel, or these little magnetic cubes that you can attach to your circular saw blade, zero it out, and then as the blade is tilted over, it gives a readout of the angle at which it's beveled. Now the ones of these that I've used, I've never owned one, but the one that I've kind of played around with showed a surprising range of movement of the blade before there was a corresponding movement of the readout. So that tells me they're not sufficiently accurate for my purposes. And the other is a universal bevel protractor. And these come in a couple different varieties, and they're made by Starrett and Brown and Sharp, and there's some modern Chinese knockoffs. And by the use of a vernier scale, they can read down to as little as 2 minutes, but most often 5 minutes, or 1/12 of a degree. Now these have some real promise. They can be quite accurate, and some of the older ones, especially the Starretts and Brown and Sharp, can be kind of works of art, but I've not found one cheap enough yet to make me want to buy it, and some of the other methods are even more accurate than the universal bevel protractor, so I haven't really added that to my toolkit yet. At the heart of all of this is a pocket calculator that can do geometric functions. Now before calculators were available, there were sine tables, and I'm sure you could still find some of those because they were printed, or you could also probably find them on the internet, but the calculator is the way to go. And this one I think was either $8.95 or $12.95 at Walmart, but it was inexpensive. And we're going to do a 45-degree angle first, so we'll punch in 45, hit the sine function. That's the sine for 45 degrees. We're going to multiply that times the length of the sine bar, which is 5 inches. And we're going to hit the equal button. And we need a stack of 3 inches, 535 thousandths high. We can, of course, ignore all those numbers back there. Getting within a thousandth of an inch is going to give us much more accuracy than we need for woodworking. Well, this is the height gauge, and I've got the spacer block under here. I've got the scale set to what the math said it should be for a 45-degree angle. We just saw that. And now I've got a 45-degree angle. I'm going to slide that in here, and that should come up right up against the edge of the square with no light showing, so we have a precise 45-degree angle there. I guess it's probably not necessary to show this, but we'll do a 20-degree angle. So we'll put in 20 sine times 5 equals, that means we need to stack 1 inch 710 thousandths inches high. Okay, so the math says that we need a stack of 1 inch 710 thousandths high. So with the spacer blocks, you always want to start at the small dimension and work up. So we need something ending in 10, so that's going to be the 110 thousandths block, the thin one. Now we've got it's kind of like counting back change. Now we've got to get up to 710 thousandths, so we're going to add 600 thousandths to that block, and then we have a 1 inch thick block. And I like to rub them on my hand to get rid of any grit that's underneath them, so that they stack together without any space between there. And of course that's a little overkill for woodworking. In a machine shop setting, you'd probably even have to be more fastidious than that. And I've taken one of the 20-degree blocks from the angle set, and we'll stack this up here and put the square here, and that should come right up to there with no light showing, and it does. So that's a precise 20-degree angle. Here's the calculation for a 22 and a half degree angle. So we got 22.5 sine times 5 equals, we need a stack there of 1 inch 913 thousandths inches high. The math for a 22 and a half degree angle says we need a stack 1 inch 913 thousandths high. So we're going to take care of the 1 inch with the 1, 2, 3 block, and then we're going to use the next to the largest adjustable parallel in that set that I have and set it at 913 thousandths. And you could do that with a dial caliper, but I'm going to use the micrometer. I've set it to 913 thousandths and lock the spindle down, and now I just need to slide that in there and slide the adjustable parallel till it fits between those faces. Tighten up the set screw and feel it to make sure that it feels right, and that feels really good. And now put the sine bar up here, and I'm going to twist it around this way because that gives it better footing. When I put it here, it's kind of cantilevered off. If I put it there, got a much better bearing surface. And then I've just taken the angle gauge blocks here, the 2 inch, the half degree, or the 2 degree, the half degree, and the 20 degree. Put those on here, and when I bring the square up to it, that should come together with no light there at the end, and it does. So that's checked out at a 22 and a half degree, a precise 22 and a half degree angle. This is where a sine bar really comes into its own, and that is to calculate, your oddball type angles. And I have a project coming up that's going to require a 14 stave turning. So I'm going to take 360 degrees, divide that by 14, and that equals 25.71 degrees. And then the miter of that would be divide that by 2, and that equals, and we'll see what that is in minutes and seconds. So that's 12 degrees, 51 minutes, 25.71 seconds. That's calculated pretty fine. So let's see what the sine of that is, and multiply that times 5. And now we need to stack 1 inch 112 thousandths. You could round that up, I guess, to 1 inch 113 thousandths, but I'm going to go with the 112 thousandths dimension. And now we'll use the planer gauge to set that height. Despite having this less than a week, this has become my favorite way to set angles, this planer gauge. I like it because it's more stable than the spacer blocks. It's more stable than the 1, 2, 3 block and the adjustable parallel, and it's a little more straightforward than the height gauge in that goofy little block that I had made at the machine shop. So I'm going to set up that angle for the 14 segment turning, and I've got a vernier caliper set for 1 inch 113 thousandths of an inch, and this is just like the adjustable parallels. I'll just slide this up until I get firm contact between the jaws of the caliper, and then tighten down the set screw here and make sure that I didn't caulk anything and that it feels good, and that does feel good there. And now set this on here, and we've got the miter angle for that 14 segment turning. But in the other cases we could check it, and that gave us we could have done that with the gauge blocks or the angle blocks alone. But in this case we've got to take this angle and somehow translate that into something that you can use for setting up the table saw. And to do that we need the sliding T-bevel, and I like these. This is a Starrett, but Lufkin and Brown and Sharp make them too, and they really hold their setting very well. A lot of times sliding T-bevels can get knocked out of alignment really easy, but these machinist type ones seem to work quite well. And they're fairly expensive new, but again, used, if you're patient, you can get them cheap enough, especially if you don't mind somebody's name being engraved on it. So I want to make sure that the blade is up inside the headstock. In other words, I don't want something sticking out. I'm exaggerating, but I don't want anything sticking out here that would interfere with it, this head part or the fence part being flat on the sine bar. So I've got that, and I'll just bring the square up to it and tighten it down, and then this can be taken over to the table saw to set the tilt angle for making the cut. Well, that's an overview of how to set angles for woodworkers, and I hope that you found something of value in this video and that you can incorporate some of these practices into your workshop. Thank you for watching.